Hey everyone, this is Enrico with Emu. Today we're going to talk about foundation walls as an example of how sometimes just relying on exterior continuous insulation may not be enough. As for many details that we show in these videos, this was an actual project where we had to coordinate some building science with the architectural and as well as the structural designs. Taking a closer look at this detail, we have a conditioned basement below and the main level of the house above. And specifically, we have the foundation wall sticking up here, and the floor is framed on top of it with the double stud wall, exterior wall frame assembly above it. This is our standard detail for this type of connection where the floor sits on top of the foundation wall. It is our standard because once we switch to the isotherm view, we can see how they flow nice and straight in this connection. Once we switch to the isotherm view, we see that it goes pretty nice and straight from the basement wall where the insulation is all inboard of the foundation wall through the floor framing up into the double stud wall above. And the isotherms go straight, nice and easy because we have the floor cavity that is insulated to the same amount or to the same plane to the interior face of where the um, insulation below is. It's not entirely to the face of the interior insulation of the wall above, but it is close enough so that the isotherms have a way to go straight through this junction detail without being too much impacted by the transition. Many of people that come and take our class are concerned about the thermal bridging caused by the floor trusses in this case. And you see that we have the isotherms are not too disturbed here by the wood. They are much more disturbed by the concrete sticking into the assembly. So as soon as the concrete stops, then the isotherms open up again and fill the whole cavity. So in other words, in this little detail, we can see how concrete is a much more impactful material to use in a detail like this than it is wood. And this is going to be very helpful to keep in mind. Concrete is much more impactful than wood for the next few details that I'm going to show in this video. As I said, this is an ideal detail where we have the floor sitting on top of the foundation wall. It's ideal for the thermal performance of this junction because we keep the concrete as low possible and we fill the floor cavity with insulation. And that was what allowed our isotherms to go straight through without being interrupted. What happens in less ideal scenarios, or what if we need to have other priorities in the design other than just the thermal performance, which is perfectly fair. Good design is always a compromise between different priorities, and thermal performance is just one of them. Now we have the ideal scenario here with the foundation wall and the framing sitting on top of it. What happens when we switch and we hang the floor off of the face of the concrete wall, like in this case? In this case, uh, probably they wanted to have the floor level closest to the exterior grade level, and so they decided to hang the floor off of the face of the concrete wall. This is something that we see often in place, especially for to make projects more universally accessible, and so to limit the amount of steps to the outside or to limit the amount of ramps between the house and the outside. So, which is great and it's very valuable. We just need to keep an eye on what's going on from a thermal performance standpoint because we may be losing performance along the way. Now that we have pushed the concrete wall further up, we can see that the isotherms are impacted and they are more squished to the inside. And you see that now the rim joist is also adding its trouble to the trouble caused by the concrete, and see how now the wood is causing a little bit extra damage as opposed to only having concrete sticking up into the detail. What happens in even more extreme cases where the level of the foundation wall comes further up past the subfloor into the wall above the exterior grade? This is a case where the grade may be higher than the wall. Maybe it is an uphill side of the house or the building that needs to be buried into the dirt a little bit for height restrictions or whatever reasons. So what happens then? Now we're pushing the concrete wall, the top of the foundation wall, further up and up from the subfloor because this might be an uphill side of the house or the building. And let's see what it looks like from an isotherm point of view. So we modeled a couple of steps. This is when we push the foundation wall up 2 feet from the subfloor. This is an uphill side of the building. Uh, and then we even have further up where we pushed it 4 feet from the top of the foundation wall. This is the actual case from one of our projects, and that is what I wanted to look into with this video with you all today. This is where we had left off our isotherms with the foundation wall coming up to the subfloor basically, and the floor was hung off of the face of the concrete wall. And once we start pushing the foundation wall further up, you see that this brings the cold further up into the upper wall. Don't say that I said that that is not really what's happening. And if we go up another 2 feet, you just see the concrete pushing the isotherms further up and further up. So this is something that becomes very evident when we start doing this type of analysis. When we start looking at the actual heat flow that occurs through this connection detail, we see that we cause further thermal bridging by pushing the foundation wall further up. And that kind of peaks at around the 2 feet from the subfloor that we saw. Once we go further up and we get into the 4 feet up from the subfloor, the heat path through the ground becomes longer, and so the heat losses become lower. So that was something interesting that we saw in this type of analysis for this specific project. What happens when we switch to a regular single stud wall with exterior insulation? How is that impacted by the same detail with the foundation wall coming up? We will see that is a lot more impacted, and then the exterior insulation is not enough to prevent issues at this junction. This is the same detail once we switch to a 2x6 framing with exterior insulation. So in other words, when we move away from the double stud wall. This wall is less insulated than the double wall that we showed earlier because there are some technical issues with having more than 4 inches exterior insulation attached to a wall. We're gonna switch to the isotherm view for this detail to see how this junction performs. You see the isotherms from the wall of the condition basement going through the frame floor detail into the 2x6 wall with exterior insulation above. And just like in the previous case, the floor cavity is fully insulated to the interior face of the insulation of the wall below it. So the isotherms can go fairly straight. There is a little bit of a change in direction, but it is not too bad. They still have time to go nice and easy through this detail. What happens when we hang the floor off of the face of the foundation wall with a single wall above grade with exterior insulation? This is what we are looking at in this detail. You see the concrete has come up just like in the previous case with the double stud wall, and then we have the frame wall straight on top of it with the exterior insulation coming down about 1.5 feet below grade. When we switch to the isotherm view, we can see we have a problem. We have the concrete foundation wall here that comes up to the subfloor basically, and the structural wall on top of it is lined up with it. That is typically how we frame buildings. And now we no longer have that continuous connection of the insulation because the foundation within the floor cavity is pushed to the inside by the concrete. So you see the isotherms are forced to do a pretty sharp curve to follow the line of the insulation. And this is very detrimental for our performance. Now remember, we have exterior insulation 2 feet down from the top of the foundation in this case, so we may be led to believe that we're good because we have continuous insulation. However, if we switch to the flow direction view, we see the heat goes in all directions, up, down, left, right, and the heat from the house or the building goes down into the concrete, goes down, jumps into the dirt, and comes back up. In other words, it bypasses this amount of exterior insulation. So this is something that even if we have some exterior insulation, heat is very capable of finding an easy way out to escape. Because we have this easy way out for the heat to escape from the inside the building into the foundation wall, down below, into the ground, to the outside, then the isotherms look like this. And these are not happy isotherms. These are isotherms that are forced to have a very sharp double switchback here. And this is going to cause a very big impact on the performance of the building. So we just looked at the case where the foundation wall comes up past the floor framing, and the floor framing is hung from the face of it. What happens if we push the foundation wall further up, just like we did with the double stud wall, 2 feet or 4 feet further up? So let's look at what it would look like. This is when we push it up. And you notice that this is an 8-inch concrete wall. We have a 2x6 on top of it. So in order to continue a finish on the inside, we assume to have to throw out some framing to support the drywall to bring it to the continuous finish. This is when we have 2 feet of foundation wall sticking up from the subfloor. And this can be the case of an uphill side where dirt or grade is higher than the finished floor of the building. And furthermore, if we go up 4 feet, this is what it would look like. Same case, just higher height delta between the outside and the inside. From an isotherm point of view, you are getting this. This is what it looks like. And you see the isotherms are not happy. This is the case of the 4 foot, and this is for the 2 feet of foundation. So it's kind of more of the same, but you see we have an issue because we have the cavity here that is left uninsulated, and we're only depending on the exterior insulation to provide this protection. But the insulation is not continuous. In this case, we were sticking to some insulation below grade, and you see heat will escape and will escape to the outside through the same path I described before. This is for the 2 feet, and this is for the 4 feet path. You know, heat will find a way to get to the outside, and please do not think that dirt provides insulation, because it really does not. So if we look at the actual heat losses of this connection, in this graph here, we have the lighter orange increase in heat losses for the double stud wall that we saw earlier. And now we have added the darker orange heat loss increase for the examples that we just saw, where we have the 2x6 wall with exterior insulation, and a lot of heat is escaping. We actually have about 40 to 50% more heat loss with the 2x6 wall with exterior insulation, because of the concrete wall is sticking up, compared to the baseline of the 2x6 wall with exterior insulation and the floor being just framed on top of the foundation wall. So this is pretty significant if you're trying to get any level of high performance. And this shows that relying on just the exterior insulation is not enough in this case. The second example that we brought today in this video, the 2x6 wall with exterior insulation, is an example that shows how if you're trying to get anywhere with the performance of your building, you cannot rely on a checklist. You really need to start looking at the actual numbers for the heat losses and performance. Otherwise, you have the cost of the additional products, the additional high performance products that you're using for your project, but you may not get the performance that you are hoping to get to. So in the next section of this video, we're going to cover how we looked into the data, and we saw a way to mitigate this risk and to actually have the performance that we're looking for. But just relying on a checklist, I have my continuous insulation, check, is not good enough if you're trying to get anywhere with the performance of your building. If we take a closer look at this detail, this is where the foundation wall sticks up 2 feet from the subfloor. I want to see where the heat is going so that I can try to intercept it and reduce the heat flow. We see that there's a lot of heat going into the wall, into the concrete wall here, down into the dirt to the outside. There are different ways to mitigate this. I basically want to put insulation somewhere on the path of this heat flow so that we can reduce the amount of heat escaping. So this area is going to be important, the face area is important, or I could do that on the outside. This is not prescriptive, this is all performance based, and it will come down to the specific opportunities of each project. Here we're trying to mitigate that additional heat losses. And in yellow here, we have added polyiso insulation in the cavity that we already called about this cavity because we want to have a flush finish on the interior. Now we have an 8-inch concrete wall and a 2x6 wall above, meaning that we have a couple of inches gap here, so we could not have um, a straight face. So we were going to furl out this wall anyway. So we may as well fill that with insulation and improve the performance overall. Because conveniently, in this case, that is where the heat gets into the concrete wall and escapes through the dirt to the outside air. So in this case, we chose this because we were already planning on this third cavity. If you're not, you can use something else to block that heat flow and put some insulation along the path of that heat escape. If we switch back to the flow direction view, we see that the intensity of the heat going into the concrete wall, in other words, the color, has decreased. And once we switch to the isotherm view, they start to look better. You see they line up better here. Um, it's not fixing the problem entirely because geometry is something that is working against us here. Geometry would be lining up these isotherms straight onto these. And in this case, because we're pushing the foundation wall up so high, we are working against geometry and we're trying to find ways to fix it, but it's not going to be as good as the ideal scenario. When we look at the intensity of the heat flow, we can see how different way to detail this junction matter. We are back to the initial detail for the 2x6 wall with extreme insulation, with the floor that is, again, framed on top of the foundation wall. This is where we have the insulation in the floor cavity and the isotherms were running straight, nice and easy. This is what we're looking at. These are the isotherms that we were talking about. Happy, happy, joy, joy. And if we look at the intensity of the heat flow, there is a lot of heat escaping to the underside of the extra insulation into the dirt to the outside. Now, when we bring the foundation wall up to the subfloor, this changes a lot, and the heat flow is a lot more intense because we have a lot of heat getting from the building into the foundation wall to the underside of the insulation to the outside. And if we're bringing the foundation wall 2 feet up from the subfloor, it becomes even worse because we have a lot of heat getting into the foundation wall, down to below the insulation, into the dirt, to the outside air. This is very typical. This is probably the worst case condition. And in this case, the cavity was still uninsulated. So we did not add that insulation in the framing here. Now, once we do that, we will see that the intensity of the heat flow goes down a bit. So let's switch to where we have the insulation. We added the insulation in yellow there. And the intensity of the heat flow is reduced a little bit where we do have the insulation. So in this cavity and in the cavity above. We don't really do much about this connection. So heat goes from the inside the building into the third 2x into the concrete wall to the outside. And really, with this kind of detail, it's kind of the way it is. Like, we can add more insulation to the outside. We can do some skirt insulation. We can bring this insulation down to the footer. But really, we are working against geometry here, because geometry is the relative position between the insulation of the condition basement below and the insulation of the frame wall above. So in this case, we may push more insulation to the outside and continue that insulation down. That insulation will need to go under and around the footer, so it becomes a conversation with the structure engineer just to have that insulation being continuous. Whereas in this case, we were not counting on that. It is doable, but it's something that we need to factor in once we want to have buildings to actually perform well. Back to our chart here, we have the same light orange um, columns from the double stud wall, the medium orange for the 2x6 wall without any additional insulation, and the darker orange or brown columns here, referring to the conditions where we added the polyiso to the interior of the wall. And we see that adding that insulation to the interior of the concrete wall does improve the performance of the detail quite a bit compared to the just a 2x6 wall with extra insulation and nothing else. It does not make it perfect. We still have about 15 to 20% extra losses. In other words, uh, we lose 15 to 20% value out of this detail just because of the relative position of the isotherms. And this is something that is very, very important to keep in mind for your project. The moment you're trying to get to high performance and to get to energy losses that are as close to zero as possible, the more these details matter and the more you cannot rely on a checklist. To summarize, what I wanted to say with this video is that we really want to take a close look at these details as we're trying to improve the performance of our buildings. I am not saying that double walls are always better than 2x6 walls with exterior insulation. What I'm saying is that there may be a belief that just because you have exterior continuous insulation, you're good. And that is not true. Details like the one we showed today show that it's very important to look through your details very carefully in the design stage so you can actually get to the performance you want to have in your project so that you don't have any performance gap later on. Thank you for watching this. As always, I appreciate you watching me geeking out about construction and building science. If you want to learn more about Passive House and our training opportunities, this is a QR code that you can use to get to know us and what training opportunities we offer, as well as we have a free info session every first Thursday of the month. If you have projects, if you have questions about training or building science, please bring them along and we can go over them together.